Now we will move into the next topic, that is random sum. Let x1, x2, xn and so on be a sequence of let me start with the IID random variables, be a sequence of IID random variables. Define the new random variable as a s suffix n, that is nothing but x1 plus x2 and so on plus x suffix capital N. I am going to define the random sum with the sequence of IID random variables, defining a random variable s suffix n as a sum of n random variables. This is different from the earlier sum of random variable in the sense I am going to make a capital N which I made it suffix that is a discrete type, in particular it is a positive integer valued random variables. N is a discrete type, in particular it is a positive integer valued random variables. I am going to make the assumption, assume that n is independent of xi's. The way we create the sum of random variables, all those random variables are mutually independent and identically distributed, and how many random variables I am going to add, that is also random. That is a positive integer valued discrete type random variable which is independent of xi's. This capital S suffix n, that is called a random sum. Then the S suffix capital N is called the random sum. You will come across many problems of this form. We will be adding many IID random variables, and how many random variables we are going to add, that is also going to be a random variable. In that case, the total number of random variables added, that is a random sum. We will go for one example for this. So, our interest is to find out the distribution of the random sum once I know the distribution of xi's and n. So, let me start with the example. Think of some queuing system in which the people are entering into the system, getting served and leave the place. There is only one person do the service. That means the number of servers in the system is only one. Because of only one server in the system, whoever comes when somebody's service is going on, he has to wait. You can think of queuing discipline is a first come first served. So, I am going to make a random variable. Let capital T be the random variable which denotes the total time spent by a customer means any person in the queuing system. Here I made a very simplest queuing system in which only one server in the system, there may be n number of people can wait. So, after the service is over, then only they can leave the system. We are interested to find out the distribution of T if I supply the information about how much time taken for customers service and what is the distribution of number of customers in the system. That means I am going to represent this capital T as a random sum in the form of x1 plus x2 and so on plus xn plus capital X, where each xi's I from 1 to n or the service time, the random variable denotes the service time for ith customer, and I make the assumption the service time follows a exponential distribution with the parameter mu. I will repeat, the total time spent by a customer in the system, that can be represented as the sum of n random variables plus x, where each xi's are IID random variables, where each xi's are IID random variable with the common distribution, which is exponential distribution with the parameter mu, where xi denotes the service time of any customer, whereas the capital X, that is the service time of this particular customer, which is independent of all the previous service time. Therefore, all the xi's and x are independent random variable. This is also follows exponential distribution with the parameter mu. I am just giving another label for x to say that that is a service time for his own. Therefore, the capital T is going to be a random sum, because you never know how many customers are going to be before him when he enter into the system. So, n is a random variable. So, I can write this small n as the capital N. I can write small n as a capital N, and xi's are going to be IID random variables including a capital X. So, now I can go for capital N is the number of customers in the system. Which is independent of the service times of all the customers. My interest is to find out the distribution of a capital T. So, I have to supply what is the distribution of the number of customers in the system also. So, here the capital N means number of customers in the system before him or his turn. That is a number of customers in the system when he enter into the system, that is capital N. So, in this case when capital N is equal to 0, That means nobody is in the system before he enters. When he enters, nobody in the system, that means a capital T is equal to x. I am going to find out the distribution of T. For that we should know the distribution of xi's as well as the distribution of n. So, we have already said the xi's, the distribution of xi's or exponential distribution with the parameter mu. Now, I am going to make the assumption of assume that the distribution of n, that is capital N is a number of customers before he enters. So, that can be possible values are 0, 1, 2 and so on. Therefore, this is going to be, I just make the assumption that follows 1 minus rho into rho power n, where n can take the value 0, 1, 10 and so on, where the rho is open interval 0 to 1. So, this is the probability mass function of the random variable n. When n takes a value 0, obviously the total time spent by a customer, that is going to be only his own service time, that is exponential distribution. Okay. So, let us find out the probability density function of capital T as a function of small t. It is easy to find out the conditional distribution of capital T given n takes some value, then go for finding the probability density function of T. That is, suppose I want to find out the CDF of capital T, that is the probability of T takes a value less than or equal to T. That is same as the conditional probability of T less than or equal to T, given that n takes a value small n, multiplied by the probability of n takes a value n for all possible values of n. Left side we started with the CDF of the random variable T, that is same as probability of T less than or equal to T, that is same as first we compute the conditional distribution of capital T given n, then by multiplying the probability mass function of n for all possible values of n, we are getting the distribution of capital T by using a total probability theorem which we discussed in the beginning for the events, but now we are applying the same concept for the random variables. That means finding the distribution of T by using the conditional distribution of T by using the sort of random sum concept, then by using the total probability theorem we are getting the distribution. But for that first we should find out what is the conditional distribution of T given n takes a value small n. Once you fix the total number of customers before him, that is going to be n, the total time spent by a customer is going to be the service time of all the n people plus his own service time. In that there is a small issue. When someone enters, there is a possibility the service of the customer who is under service, it may be keep going and it may need the remaining service time for the customer who is under service plus the fresh service of the second customer, third customer and so on till the nth customer, then plus his own service. So, again I am going to use the logic of exponential distribution. since the first customer under service whose service is a exponential distribution with the parameter mu, the remaining service time, that is also going to follow exponential distribution with the parameter mu by using the memoryless property. That is a conditional probability of x greater than t plus s, given that x is greater than s, that is same as probability of x is greater than t. That means that the past history is erased, and the conditional probability is again going to be the probability of x is greater than t, which has the same distribution of exponential distribution. Therefore, the total time spent by a customer when already n people are in the system, that is going to be remaining service time of the customer under service plus fresh service of n minus 1 customers plus his own service. That is capital T is x1 sort of tilde means remaining service time plus x2 and so on plus x suffix small n plus capital X. Each service time is exponential distribution, identical, mutually independent with the x. Service is one followed by the other. Therefore, you can conclude for a fixed n. So, this is the distribution of t for a fixed n, that is gamma distributed with the parameters n plus 1 with the second parameter mu. This is one of the important properties of gamma distribution. The gamma distribution, which has the parameters whenever it is a positive integer and the other parameters mu, that can be visualized as the sum of mutually independent exponentially distributed random variable with the parameter lambda. There is another name for this, that is Erlang distribution with the n plus 1 stages with each stage of exponential distribution with the parameter mu. So, this is a conditional distribution of t given n takes a value small n. Therefore, we know what is the probability density function of t given capital N takes a value n, that is a small t as a function of n. That is a mu power n plus 1 t power n e power minus mu t divided by n factorial. It is a gamma of n plus 1, therefore, it is a n factorial. So, this is valid when the t lies between 0 to infinity, 0 otherwise. This is basically a gamma distribution with the parameters n plus 1 comma mu. Now, we are going back to finding out the CDF of t, that is probability of t is less than or equal to t, that is same as the summation n is equal to 0 to infinity. The above one is a conditional probability density function of t given n. Now, we need a conditional distribution. So, therefore, it is a minus, instead of minus infinity, you can go for 0 to small t mu power n plus 1 s power n e power minus mu s divided by n factorial multiplied by 1 minus rho into rho power n ds. This is a good example of introducing the conditional distribution, random sum, and the properties of exponential distribution and the gamma distribution. If you do the simplification, one can get the answer, that is 1 minus e power minus mu times 1 minus rho times t. So, this is a CDF of t for t greater than or equal to 0, otherwise it is 0. It is a CDF of capital T as a function of small t, that is 1 minus e power minus mu times 1 minus rho times t. With this we are completing the module of functions of several random variables, starting with the distributions of functions of several random variables, then order statistics, then as a third lecture conditional distributions, and finally random sum.